That was great. And then now we're going to pass it off to Ravi Startzl. And if anyone has any questions for Keval, feel free to ask them in the chat.
Great, thank you very much. Can you hear me okay? Okay, super. I'll go ahead and share my screen here. So the topic that we're talking about today is generative artificial intelligence in the domain of cyber operations. And I think that this is just about one of the coolest subjects or areas ever. In the context of, say, graduate student professional development, I think it shows one of the interesting growth areas or one of the interesting domains in which the recent surge in interest in artificial intelligence can be applied to for a lot of low-hanging fruit and benefit. And I actually have two slide decks here, so I'll go through this kind of initial one where I'll explain some of the ideas behind it and then discuss a little bit some of the actual work that I've done in this space, and hopefully it will fire your imagination and you can start to engage with things like this as well. Overall, I kind of want to just take a moment and just give you a little bit of background about myself. So I'm a PhD in machine learning and artificial intelligence from, in fact, let me go ahead and share a different deck just so you can give you a little bit of my background. So I have a background in politics and philosophy, believe it or not. And I have a PhD in machine learning and artificial intelligence, as well as a master's from Carnegie Mellon University. And I've always been an addict to solving or at least attacking hard problems, even if sometimes we don't get all the way to a good solution. It's always a learning exercise to tackle something that hasn't been done before and that's really hard to do, and you have to be creative in the approach. And I think that the most effective by far way of doing problem solving and approaching and tackling problems is to first ask yourself, how did nature solve this problem already? And where in nature has it been solved? And then how do I simply adapt what evolutionary intelligence has already figured out to my particular domain or problem? And in that way, I can just shorten the work cycle and the creative loop quite a lot. So let me go back to the other slide deck for 1 second to be able to, in fact, I'm going to stop sharing altogether because I think I'm getting a little bit mixed up here. Okay, great. So what we're talking about with generative AI and cyber operations is essentially the capacity to see everything everywhere all the time all at once. And I know that that's a lot to take on or a lot to take in, but it is an astonishingly important concept, because the traditional limitation or the traditional problem is one of span of control. And the AI as a buzzword has become so pervasive that it's almost hard to understand what people mean by artificial intelligence anymore. There was a time when the word artificial intelligence usually referred to a specific kind of approach using deep neural networks, and you kind of had some idea of what people meant by it, usually within a certain kind of school of thought or context. But now it's just become a kind of universal buzzword. So I think we need to try to work past that, work past the hype, and figure out what it's good for. One of the things that I think is a non-perishable characteristic of artificial intelligence that really is going to be useful for the long term is its capacity to manage complexity. The world that we live in today is really just way beyond human scale. Almost everything about the world that we live in cannot actually be understood by individuals because there are just too many moving parts, too many components, from our supply chain to how our military works to virtually any field of medicine. It's just really too complicated anymore. And so I have a very optimistic and you could say positive view of the potential impacts of artificial intelligence, because I believe what its real non-perishable characteristic that will help us is that it will help us wrangle a lot of that complexity into spans of control of elements or items of information that we actually can get our heads around. And so, you could say this typical span of control for a human being is somewhere between 3 and 8 items at a time. We can only keep 3 or 8 things in mind at once, between 3 and 8. whereas the number of free variables or moving parts in any reasonably complicated system is many times larger than that. And so artificial intelligence will fundamentally have the capacity to bring the right information to the right place in the right format at the right time to facilitate the mission that you're trying to accomplish. And let's remember, artificial intelligence and is really a form of machine learning, and so that means it really requires an objective task or an information need in order to function properly. There really is no such thing as machine learning or artificial intelligence without an objective function. That's just descriptive. That's just describing the world, descriptive analysis, descriptive statistics, what have you. So in this context of, I think one of the most important areas that is getting increasingly complicated, increasingly risky, and therefore would increasingly benefit from the application of AI is cyber operations, or specifically the capacity to manage the complexity intrinsic to cyber operations and create synthetic cyber teams where there's a human and an artificial intelligence working hand in hand to handle the tasks that, a typical cyber operator would normally have to handle by themselves. And so this slide says it all, which is that the cyber threat landscape is rapidly evolving and rapidly becoming something where anyone who has AI augmentation in it is going to have a vast strategic advantage over anyone who doesn't. So the thing about the way artificial intelligence works is it looks for what it has the ability to do is extrapolate on existing trends. So historically, machine learning techniques were able to identify patterns that seem to match known phenomenon, or might be able to identify anomalies that diverge from known acceptable operating parameters. And a lot of that algorithmic problem solving or pattern matching was embedded in these system information and event management platforms, which are kind of clearinghouse, a kind of they're basically a desktop application that cyber operators run on their computer. And they are connected to a server system or whatever system gateway is being protected or monitored. And anything that appears out of the ordinary is brought to the operator's attention, and then they have to go through some kind of procedure to investigate and resolve the incident or event or potential issue. But it's really, even with that extra instrumentation and augmentation, the scope, scale, and velocity of these kinds of events is moving beyond what SIEM platforms can handle. And it's certainly moving beyond what the human operators on the other side of the screen can effectively manage and handle. And so we need to be able to manage this complexity with greater speed and also with fewer false positives. And that means intrinsically we have to adapt to increasingly complex systems and be able to pull the relevant information out. I'm couching this in terms of a defensive kind of protective operation, but the truth is our adversaries are going to be using this in an offensive capacity as well. And artificial intelligence as an offensive tool is a real risk, and it's a real thing that has already started to kind of emerge in some corners of the world. And if you have an imbalance between the offensive and defensive sides of things, then whoever has the AI is going to tend to prevail. So I have a deep interest in helping to try to make that situation better for us. And so a lot of the work that I'm presenting here is work that I've done directly with Army Cyber Institute, or Space Operations Command, or Delta 7 from the Space Force, and it's ongoing. So I'm happy to present, kind of this high-level information, but if you'd like to talk more about this kind of work or those kinds of organizations and what they're doing, by all means, I'm happy to follow up, not only in questions, but after this presentation. And so the arc that we'll be taking is I'll just define some terms. I'll talk a little bit about the relevance, as I've already done, to cyber operations and what synthetic cyber teams really are. Talk a little bit about some of the specific use case scenarios or applications in cyber operations and how to build generative AI capabilities into your team. So the first thing I want to just do is, for anyone who isn't fully familiar with artificial intelligence, modern artificial intelligence systems in the form of large language models and transformers, is just give a very high level, kind of cartoon level overview because you don't need to know the technical details in order to understand how they work. But it is extremely helpful. And generally speaking, what a modern AI, what people mean when they refer to modern AI is a large language model based on a transformer architecture that has been trained on a large amount of unlabeled text using the self-supervised masking training method, meaning what happens is there's like a rolling window and you have a stream of sentences coming into the model to be trained, and there's not enough people in the world to label all of the text on the internet. OpenAI was trained at least on 80 terabytes of raw text for their GPT systems, and probably more in reality behind the scenes. And so when you're dealing with data of that scale, I mean, 80 terabytes of text is an astronomical quantity. And so when you're dealing with data at that scale, there's no chance of having humans label that data. And so the clever trick to turn that massive unlabeled and therefore kind of hard to use information into something that actually is usable and able to make good predictions, a good generative output, is they just copy the text and then randomly blot out words or tokens in this case, because they trained on something that was slightly smaller than a word in order to fix the prefixes and suffixes problems. Meaning you want to be able to recognize the word and not have the fact that there's a suffix or a prefix distort the fact that you're recognizing a word, and tokens help with that. So, the trillions of tokens across that amount of data, and they randomly block them out and then force the AI to try to guess what the word that has been blocked out is. It's a really elegant, clever way of folding data back on itself to be able to kind of get labeled information out of something that's fundamentally unlabeled. And that it turns out to work extremely in an extremely compelling way. And I think one of the side effects of this is that we kind of need to come to grips with at a bigger scale that we're no longer the only cognitive entities working in cyberspace. Artificial intelligence is limited as they are still, and certainly we do not have general artificial intelligence today. There's been a paper that from Microsoft discussing sparks of artificial general intelligence seen in some of its AI systems. I'm skeptical. I don't personally think that we've seen artificial general intelligence. I think what we've seen is an interesting reverberation or an interesting echo of human intelligence that the machine learning system or AI system has actually extracted from the text through its analytic process and presented back to us. And we see it as the AI looking somewhat intelligent, but in reality, it's just finding latent forms of intelligence that we've encoded in the text that we've actually put out on the internet. But be that as it may, AIs are getting they're at human levels of performance in many problem tasks already, even if they're not creative and autonomous, and even if they can't maintain coherence for long periods of time like humans can. On specific limited tasks, they can easily achieve human level performance on a wide variety of problems already. And so we're not the only things that are capable of thinking anymore. And so we kind of need to come to grips with that as a larger body of people, and start to ask more important questions beyond the technology, like what does that mean for us from the perspective of ethics? What does that mean for us from the perspective of having virtuous principles guiding our institutions, and how do we safeguard against the erosions of civil liberties? How do we safeguard against the erosions of other values that we might hold really dear as people become supercharged, or as groups of people become supercharged by the capabilities presented by AI? And of course, cyber operations is probably ground zero for all of that. So how you actually utilize an LLM is it's a complicated process when you get into the weeds, but it's a very simple process at a high level. And that fundamentally is that you take your training data, which in the context of most large language models is just text, and then we transform that text into vector embeddings, which is really just a way of turning words into numbers so that the artificial intelligence can understand the relationship and compute numerical quantities between elements of the text, like the relative importance of tokens to each other as used in the attention metric. And then and the whole idea behind using a vector embedding space is to turn a sentence or a passage of text into a number line, and stack these number lines where each line essentially represents a fixed passage of a size of text. And the concept behind how the vector embedding works, the transformation that turns the words into numbers, is such that it is intended to cause birds of a feather to flock together, which basically means similar concepts on a meaning level basis appear close to each other in the topology of the number space of the vectors, and very dissimilar topics appear very far apart from each other numerically in vector space. And this is really the substrate upon which the artificial intelligence system does all of its further learning and creating the weights that are in the neural network that it actually learns based on the input of that vector. And then your prompt gets converted into a vector as well and synthesized with all of the effectively all of the training data that the system has been trained on by virtue of the fact that it's developed weights over the original training vector space. And then it takes your prompt and it takes the weights that it has, which are based on the underlying training data, and it synthesizes a new vector out of those two things using a simple math operation called a dot product, which just means element-wise multiplication in a vector space. So basically it reduces it's a form of matrix multiplication that reduces essentially two different sets into a single number, and that number represents how similar these two vectors are, or how similar your prompt is to any given set of training data that the system has seen before. And so when AIs are producing their results, they look quite creative and they look quite compelling because they're fundamentally taking what you said, combining it with what someone else on the internet said about something very similar or relevant to you, to what you're saying semantically, and then forming a new sentence that is a kind of synthesis of those two things. And so that's why it looks and sounds intelligent, and that's why it can be very useful. The question of intelligence is really kind of beside the point. Utility is really the key thing in my consideration here. But it looks intelligent for that reason. And so the vector embeddings are conducted in such a way that, generally speaking, the more specialized or the more focused on topic space, the better your outcomes will be. So getting a good vector embedding space can be just as, if not more meaningful to good artificial intelligence performance as the actual training of the artificial intelligence itself and the choice of neural network and transformer architecture that's used. And the intuition behind and really the secret key ingredient that's allowed neural networks to kind of come up to this amazing level of performance is what's called attention. And there was a paper published called Attention is Everything, in which they describe this phenomenon in detail. But essentially what it's doing is giving context to language. So if I say something like, I love red apples, what the attention mechanism allows you to do is it allows you to gauge the relative importance of words to each other. So, for example, I has a significant degree of relevance to love. I has a significant degree of relevance to apples, but a lower level of relevance to red in this particular example that I'm showing on the screen here. So, and so on and so forth. So you build this entire matrix, and essentially once you go through the process of calculating that matrix, you calculate the cosine similarity or the dot product, which is a measure of relatedness, and the more similar, the smaller the degree of difference between those two things, and you're off to the races. And so once you put these pieces together, you're able to generate a response essentially to any kind of input. It could be words, it could be clusters of pixels, it could be sound waves, it doesn't really matter. Because that transformer architecture just assigns relative meaningfulness to any collection of objects. It doesn't have to be only text, right? And it can be across mediums. It can be text to sound. It can be sound to image. It could be a whole different range of multimodal combinations. So the relevance to cyber operations is that I believe we have a clear and present danger to us today. And I know that cyber operations and cybersecurity sometimes is a challenging area because it requires a lot of practical experience, and it's something that's hard to train for, but that doesn't mean it's not a super critical and important area. And regardless of whether you work in this area or not, it's actually an awesome area to learn in. If you actually can go use it as a way of gaining experience with tracking, networking routing protocols with coding, and then it's totally worthwhile. So I encourage everyone who's a student to experiment with it. But I think the clear and present danger is that hackers who know how to use AI are vastly more dangerous than hackers who don't use AI. And the reason is because they can collate so much more information so much more quickly. And because of that phenomenon that I was describing earlier, where AI can appear to be intelligent by leveraging essentially all of the text that it's been able to read off the internet, especially in the case of like GPT or equivalent systems like that, it also means that hackers who utilize AI are going to be able to instantly, effectively know everything every other hacker who's ever published anything knows on demand. And so that means you're able to bring a vast quantity of knowledge to bear on any particular problem, really on in real time. And so to address this, I think we need to create synthetic cyber teams, and this is an active area of research I'm engaged in, where we're effectively creating teaming systems where you have a human here and an AI here, and they're kind of partners, and they're peer partners. They're almost pair programmers in a certain sense. And the human helps give coherence, direction, ethical guidelines, rules of engagement. It brings all of those things to the table. And the AI brings extremely fast problem solving, extremely fast computation, instantaneous access to knowledge, those kinds of things to the table. And between the two, they're just immensely more effective than either one on their own. So there is a vision that eventually one day we'll reach full cognitive systems, but we're not there. And the main reason that we're not there just on a phenomenological basis is because AIs, well, if you'll excuse my way of saying it, AIs are just kind of batshit crazy most of the time. And they really require a human to draw out the best part of the AI to apply to a problem. And the reason for that is because all AIs are born obsessive compulsive psychopaths, because they overfit. Deep neural networks overfit almost by nature. And so the human really has to be there to allow the AI to operate in a productive way. And that'll be the case until some next major breakthrough, which is probably years in the future. Although AI is moving very quickly in derivative engineering, AI is not moving very quickly in fundamental insights into the nature of complex systems or into the nature of cognition. And so we need to make more advances in those areas in order for the next attention is all you need paper to come out to allow the next major quantum leap. And so don't get FOMO, don't get fear of missing out, because the fear of missing out is definitely not, you're definitely not missing out on anything. There's plenty of time to get into artificial intelligence and move forward. So there's a variety of ways in which cyber AI can be employed in cyber operations. I think cyber exploitation planning is a very clear way. It takes a long time to create an attack plan. An AI can generate an attack plan in minutes with your prompt feedback, and it can dynamically adapt attack plans in real time. This is a clear area of application. One thing that I did just as I went out to CVE details, and I have a gaming computer with 3 GPUs on it, and I used a simple open source stack with Hugging Face and even an old LLM called Flan from Google. And with just 198,000 reports and about 1 million peripheral pages that were linked, I was able to create an AI with which I was able to have a conversation to find extremely bad security vulnerabilities that I knew nothing about, but that if I were doing, let's say, a network port scan on a network, and I could just find out what version of an operating system, what patch level, et cetera, from just the network, I can feed that information into one of these homegrown AIs, and it can feed back to me all of the known vulnerabilities for that particular system, which could then lead into an attack plan development stage, so on and so forth. So the other place where these things have had a tremendous impact is in social engineering, spear phishing in particular. These things can create very compelling fake messages to get you to believe that you need to type your password in or you need to divulge some personal information. And this has become a huge problem. I'm less at risk because I know about it, but my parents are tremendously at risk. My grandparents have no hope of resisting a spear phishing attack. So there's a wide range of risks associated with that kind of approach. The other area that I think AI is going to make a huge difference on is threat intelligence. Being able to do attribution is a major problem in cyber operations. Who's responsible is a non-trivial question. And artificial intelligence may be able to move the needle on threat attribution in a way that human teams have been struggling to do. And certainly, even if you can get good attribution on any one attack, you can't actually do threat attribution analysis as part of your standard operating procedure because it's just too intensive in resources. So AI might be a great way to actually do more of that more effectively. So I think I've mostly covered everything I want to, and there's like 3 or 4 minutes left. But I'll just end with some points here that I think are useful for everyone, not just for people looking at building synthetic cyber teams, which principally right now are the U.S. government. Although it should be every company. Not every company is paying attention to this question. Building teams of experts. I mean, really, AI, we are far away from Skynet. AI is not going to come destroy the world, but I would be worried about the unscrupulous actors who can leverage AI to supercharge their agendas. Those are legitimate and deep threats, and our teams of experts are needed to help in our subject matter areas and in the areas that any individual department or group is working in. You need your subject matter experts because the AI is not magic. It's built on collections of information and it's built on expert knowledge. And then I think having concrete use case scenarios are extremely important because artificial intelligence as a buzzword has the risk of becoming hyped, and hype never really translates well to utility. So focus on utility first and focus on doing something interesting and then worry about the hyping of something that actually is useful. And then continuous learning and improvement is just something like for any students who are here right now, you're going to graduate, move on. It's probably more important for you to continue your learning journey after you leave school than even while at school. Because these technology stacks move very quickly, the companies move very quickly, the demands and requirements move very quickly at a high level. I mean, like what's even being asked for from companies like Splunk, for example, has evolved tremendously in its time. And just look at Microsoft today versus Microsoft 5 or 10 years ago. I mean, it's hardly even recognizable. So learning always allows you to stay on the front edge of what's happening and always stay relevant to the current challenges. And I think you should adopt the lifelong learner attitude early and stick with it. So I'll go ahead and stop there and answer any questions anybody has.
Yeah, I do have a very thanks Ravi, great talk, and I think I'm glad that you're working on something that's really crucial and of really good interest to me, right? Splunk also being a CM product, is going to face this challenge very soon. And so I think I have a specific question for you in terms of your work that probably you're doing with the military. Like you said earlier, right, having the right vector embedding space set is very crucial, right? The more domain-specific data you have, the better results and a better attack plan. So, in terms of having cybersecurity data, how easy or difficult is it to get instances and data points which might not be publicly available, which are sensitive, which the government can't share up, like CV details, which is available to everyone, right? And how risky is it to like let your model have access to it? Especially when it's going to be a public-facing model.
Yeah, I think it's just a matter of time until a cybersecurity or cyber operations specific vector embedding scheme is created, because it has very unique uses of language, and the chains of causality and the kind of grammar even that's used is different from normal language. If I have any luck, I may actually be the one releasing that, the first version of it. I think there one overlooked source for information on this is the Common Crawl frequently. And so I actually have a rack in which I've downloaded about 120 terabytes of text data from the Common Crawl. and it's being processed to extract relevant cyber operations content, which goes a long way. It's all publicly available, but at scale hard to get to because of that. As far as getting access to, say, classified or secret or confidential systems, whether it's government or private, I don't think there's really any risks to allowing your model to learn from it. If you're using it internally, the risks are who gets access to that model. If this is a model that's going to then be turned around and shared in some fashion, or that data is going out over the wire to a service through an API call, then there's intrinsic vulnerability there because especially with API calls, those can be intercepted, and in fact, there's a little bit of back and forth on poison data injection attacks. But if you knew the kinds of phenomenon that your particular company's security AI was looking for, it would be really trivial for an adversarial AI to design the perfect attack against the security AI. So I would say you need to have either on-premise or in some way that's very secure security models. You can't share them because the risks, and even if you had very carefully delineated perimeters in a cloud computing system, it's just too painfully clear that cloud computing networks themselves are not actually intrinsically secure. So there's like nested layers of attack that could happen. So I don't know if that answers your question, but it's generally by limiting the amount of topics that have to be covered, you reduce the context, which means every combination of information, every combination of words and is more meaningful to the context that you're in. And so I hope that answers your question.
Yeah, definitely. I think that makes sense, right? And I think it in the end, it just boils down to the owner having a very secure environment to keep that model, which has access to sensitive data in.
Yeah, I think if we get into this kind of negative thinking cycle where we're like, oh, there's a risk, we can't do it. Oh, there's a risk, we can't touch it. Then we're just kind of in a race to the bottom. All we're doing is we're waiting for someone who isn't afraid to experiment to come and actually eat our lunch. We have to take kind of this responsible effort to do something about these very clear and present and apparent risks. But at the same time, we have to be cognizant that this is largely uncharted territory. So take all the precautions, but expect some teething pains. Expect some growing pains.
Thanks.
Amazing. Thank you both so much for joining on Zoom. We really appreciate it. We'll send out this recording to our students. We know that they're pretty wrapped up right now. There's an event simultaneously going on just almost immediately after this. So we really appreciate your time and hope you have a good weekend and stay warm, because if you're in Colorado, it's going to snow soon. So.
We're in pulse modulated summer winter territory.
Yeah, it'll get warm again before it gets cold, but we got to get through that snow. All right. Awesome. Well, thank you so much. Have a good rest of your day.
You too. Thank you.
Thanks.